In the first part of this question, we have to explain why the frequency of the electromagnetic radiation, which is presumably coming in like this and hitting the surface, has to be higher than a certain value. This is pretty straightforward because we know that the energy of a photon is equal to hf. In other words, it's directly proportional to the frequency. So the higher the frequency, the more energy the photon has. We also know that a photon can either be 100% absorbed or not absorbed at all. In other words, it can only pass all of its energy or none of its energy to one of the delocalized electrons in the surface of the metal. Therefore, since the electrons in the surface of the metal require a certain minimum amount of energy to be released, that of course is known as the work function, it therefore stands to reason that in order to get that minimum amount of energy, there must be a minimum frequency of photon that is going to affect the emission. I want to spend a moment just explaining where current in this circuit actually can come from. So first of all, let's imagine that we have a switch in this space here and that the switch is open. That means of course that no current can flow and that there is therefore no potential difference between the two electrodes up the top here. Now if we illuminate the surface of the photoemissive electrode with some EM radiation, such that it has an energy which is quite a lot greater than the work function, we know that if that's the case, some electrons will come shooting off of this surface. And some of those electrons, but not all of them, will arrive at the wire electrode on the left, therefore as it were pushing the other electrons along in the circuit. Now this means we have current because something is being pushed on here and something is travelling across the gap, i.e. an electron from the surface of the photoemitting metal. Therefore we have a small current. Notice that it is indeed a small current because the meter says we're measuring microamps. Now, as if by magic, I've removed the switch and we're going to assume that this terminal is positive and then this one is negative. That means that our wire electrode up the top there is going to be positive too. Now this means that electrons will be attracted across that gap and are more likely to hit the electrode because they're being attracted to it, and therefore we'll get a more significant current. We'll talk maybe about what happens if the positive electrode here is actually negative a bit later on. We've seen then that electrons are coming off the photoemissive surface with a range of kinetic energies, but perhaps what might not have sunk in yet is that they're also coming in with a range of directions. In this question we've been asked to determine the number of photoelectrons per second leaving the photoemissive surface when the current is at its maximum, i.e. this value here. Now the current is going to be at its maximum when every single electron that is emitted from the surface is able to arrive over at the anode on the left hand side. All the electrons, if they are going to miss that anode, are actually attracted to it strongly enough so that none of them miss. The maximum current is exactly 30 times 10 to the minus 6 amps. And we remember that 1 amp is the same thing as 1 coulomb of charge flowing in a second. Now interestingly, we have 1 second noted in our question. But instead of 1 coulomb flowing, we actually have 30 times 10 to the minus 6 coulombs flowing. And if we divide that therefore by the charge on each electron, which is 1.6 times 10 to the minus 19, that will tell us how many electrons have travelled across the gap. And that comes out as 1.9 times 10 to the 14 electrons per second. And really, I should put the symbol for an electron in there. Next, we've been asked to explain why we get the flat plateau of a constant value for current at certain values of positive V. And this comes down to the fact, as we've said before, that electrons are leaving the surface in different directions with different kinetic energies. So some of them, if there's no potential there, will just miss the wire electrode. So if you make that electrode on the left there positive, then even those electrons that we're going to miss, if the potential is high enough, will eventually get pulled in and hit that electrode. And so at this point, which is around about half a volt, every single electron being emitted from the photoemissive surface is arriving at the anode. Lastly then, we have to explain why it is that if the wire electrode on the left is made negative, as we increase the value of that negative, so the current reduces eventually down to 0. Once again, this depends on the fact that our electrons are being emitted with a range of kinetic energies. So here's one with a lot of kinetic energy and one with not so much. If you think about it, of course the wire electrode is going to be physically enormous compared to the electron. So let's represent that by this big blue circle and shove a negative in there because we know it's at a minus potential difference. Now this means that the top of our two photoelectrons, the one that has a lot of kinetic energy, is going to have enough kinetic energy to overcome the repulsive force between the electron itself and the electrode. Therefore, chances are it will actually hit the cathode and contribute to the current. For the other electron, which has less kinetic energy though, let's assume it doesn't have enough kinetic energy to overcome the repulsive forces. Therefore, it's going to deflect downwards or perhaps even back to where it came from. So as we increase the size of this negative potential, in this case up to about 1¼ volts, we will see that more and more of the electrons are being repulsed away from the cathode, and eventually we'll reach a point where none of the electrons arrive at all at the cathode and the current drops to 0. And this is what we call the stopping potential. Let's write this out like a mark scheme. So our first point would be to say that the photoelectrons are emitted with a range of kinetic energies. Our second point would be to mention the repulsive force between the electron and the negative electrode. The third point then is to say that as the potential difference becomes more negative, so more electrons are repulsed enough such that they fail to arrive at the electrode, and so the current falls eventually to 0.